whenever we cannot get the complete information from a population, maybe due to financial difficulty, maybe due to time difficulty, we may collect data from a subset of the population. And when we do the subset information collection, that is known as sampling. So I will give one example here. A researcher takes a sample of 50 male employees, finds that their stress level is 6.3. And again, he collects another sample of 40 female employees, finds that their stress level is 7.1. Now, can he conclude that the mean stress level of genders differ? Means a stress level of females is more here, stress level of male is less. In that case, can he say that maybe females suffer more from the stress? Means he's generalizing what he observed in the sample to the population. But here one problem comes. Instead of this 50, if some other 50 students, 50 people, employees respond, is he sure that he will get 6.3 as mean? Is not sure. Now, instead of this 40, if some other 40 females respond, is it guaranteed that he will get 7.1 as the mean? It is not guaranteed. Means different samples can give different estimates. If so, then how can you generalize what is obtained from the sample to the population? I'll give one more example to make it more clear. Say, for example, I have a small set of 6 people in a class. Their marks are 2, 6, 3, 5, 8, and 9. So the total is 33. 6 students are there. 33 by 6, 5.5 is the mean of the class. Now, instead of taking this population, suppose I proceed by taking samples of size 2. So sample 1, I'm getting the values 2 and 3. So you can see 2 here, 3 here. That came 2 plus 3 is 5 divided by 2 observations. I get mean 2.5. Suppose another sample, total 14 divided by 2, I get 7. So you observe that the first one, mean 2.5 is lesser than the population mean. Second one, mean is more than the population mean. Imagine a third sample coming, 5 and 6, total 11 by 2, 5.5, which is exactly same as the population mean. So some samples will give correct information, some samples will give biased information. So this we call fluctuations in sampling. Now, then the thought comes to me, how shall we overcome the problem of fluctuations in sampling? Means, as a researcher, I will take only one sample. And with that information, I'm generalizing. And if it is a biased one, what will I do? So I need some other mechanism by which I may know that the information I got from the population is reliable. And that is called testing of hypothesis. So in short, testing of hypothesis is a method by which we may determine with certain degree of confidence as whether information is due to fluctuations in sampling or not. So in short, it is just a method by which we will come to know with certain probabilities attached the information is due to fluctuations or it's a real one. Now, In order to learn this method, there's a lot of terms, terminologies. We need them together. At the end, the technique evolves. So let us try to understand the notations, terms, terminologies, and all. So first thing, sample mean means mean calculated from the sample is denoted by X bar. And if the mean is calculated from population, it is denoted by mu. So mu, whenever we are talking about population mean. X bar, we are talking about sample mean. S is the sample standard deviation, and sigma is a population standard deviation. Again, here that difference is there. N is a sample size. So then the first thing I want to define is hypothesis, an assumption about population which may or may not be true. So for example, if I am saying Rama is a good student, can it be a hypothesis? It cannot be a hypothesis because it is an assumption about an individual. But if the assumption is about a population, it becomes a hypothesis. So an example I can give, mean height of an Indian is 5 feet 7 inches. It may be true, may not be true. So, but it is an assumption about the Indian population. So this is a hypothesis. Now there are two different types of hypothesis. One is null hypothesis. We denote it by H0. It's a neutral hypothesis which is stated with the intention of nullifying it later. For example, webinar is equally effective as classroom teaching, which may be true or may not be true, but it is a hypothesis. And here, I'm not taking any side. I'm neutral. I'm not saying webinar is better, nor I'm saying classroom teaching is better. So here, please note that neutral is the keyword to be used. And then alternative hypothesis can be there. Anything contrary to the null hypothesis is alternative. For example, webinar is better than classroom teaching. That can be one. Classroom teaching is better than webinar. That can be another. The methods differ in efficiency. Say here, third one is not specifying which is better, but it says both are different. So the first two are examples of one-tailed test, whereas the last one, two-tailed test. See, the first two are preferring one side. So later on, we will refer to them as one-tailed test, and the second one will be referred to as two-tailed test. Now here, please let us underline the keywords. Say, first one is a neutral hypothesis. So here, what is a null hypothesis? Please remember that it's a neutral hypothesis. Okay, alternative hypothesis means anything contrary to the null. This you need to remember. Okay. Okay, we go to the next one. Through testing, we can accept one among H0 and H1 and reject the other. Means we have some calculations. At the end, we will say we are going to accept H0 or we are going to accept H1. So in this process, there can be some errors. Let us analyze that possibility. Suppose if H0 is true, and if I reject H0, that is a mistake. Whereas if H0 is true and I accept H0, that's a correct decision. So here, this is called type 1 error. And then H0 is false, I reject it, that's a correct decision. But H0 is false, still I accept, that is an erroneous decision, which we call type 2 error. So in words, if I have to say what is type 1 error, it is like this. Rejecting H0 when it is true is known as type 1 error. Similarly, type 2 error is accepting the null hypothesis when it is false is type 2 error. Now, both errors cannot be minimized simultaneously. Why? Because if I want to reduce type 1 error, I have to reduce a chance of rejecting H0. If I reduce a chance of rejecting H0, it will increase a chance of accepting H0. That will increase a chance of type 2 error, and vice versa. So that is the reason we cannot minimize them simultaneously. So the maximum probability by which we risk a type 1 error is known as level of significance. So actually this alpha, the researcher has to specify in advance, maybe 0.05 or 0.1 depending on the situation. If one has to be more accurate, then they may fix at 0.01. That means 1% error is allowed. 0.05, that means 5% error is allowed. Now, it is also the probability of rejecting the null hypothesis. Now, to continue with this study, we need to understand what is known as normal distribution. Say, it is one among the many standard distributions in statistics. Actually, we need to know 3 standard distributions in this section. One is normal distribution, another is t-distribution, another is chi-square distribution. Now, what are these distributions? Of course, a lot of mathematics is behind that. But being applied science students, we will be just looking at how it can be used. So we'll have a vague idea or a broad idea of what it is. So to introduce that concept, say I'm bringing in a histogram. You know how histogram is created. First frequency table is created. And after that, what we do, we put the class width, and across that the bars are erected. Now, if you have such a histogram at the center onwards, if I draw a curve like this, so I get a frequency curve. Now, height, usually what happens is those people who are extremely short, they are extremely less. So frequency here will be less. People who are extremely tall, they are also extremely less. So frequency is less here. Whereas people who are extremely, who are having average height, they are more in number. So frequency is more there. Most of the people are near average or on the average height. So their frequency is more. So thus we get this bell-shaped curve. So we have a bell-shaped curve, and it is symmetric about the mean value. This is mean mu, and in notations, how do you write? X curl, we write curl, but it has to be read as X follows normal distribution with mean mu and standard deviation sigma. So that the role of this mean and standard deviation we'll see later. Area under the curve between any 2 points A and B represents a probability that X falls between A and B. Look at this sketch now. I'm marking A and B. The area, this area is the probability that X falls between A and B. Now, total probability is 1, therefore total area under the curve is 1. Area to the to each side of mu is 0.5, means from this to the right side it's 0.5, and from this to the left side also it is 0.5. Understanding mu and sigma, the two parameters. Okay, so here we'll try to understand the mu. What's the role? Arithmetic mean. Say for example, consider the height of Indians. The mean height is 160 centimeter. So it will be normally distributed. Now consider some other ethnic race are taller than Indians. They will also have a curve which is symmetric, but their location will be above us. So ours 160, theirs 170. Consider another ethnic race, say for example Tibetans. They are shorter than us. Their curve also will be symmetric about some value, and that value may be lesser than 160. So in short, arithmetic mean tells the location of the curve. Then standard deviation determines the shape of the curve. So for example, if you have a flat curve like this, that means it's a large standard deviation. If you have a peaked curve like this, you have a small standard deviation. Now, standard normal distribution, another concept is standard normal distribution. So here, that X which is normal, it is there. From that variable, I'm subtracting its mean value. So if I subtract the mean value, what happens? Half of the observations will become negative, half will be positive. And divide that by standard deviation. So when I divide by standard deviation, say for example, X is in centimeter, divided by standard deviation, which is also centimeter. So this particular Z which you get, it will be free from the unit. Okay, and also that curve will have 0 at its center. So this is known as standard normal distribution. Why this is brought in? The reason is that for calculations, we need area under the curve. And for there can be infinite number of mu, infinite number of sigma. We cannot print standard tables for all such values. So what the statisticians have done, they have printed standard values only for standard normal distribution. So whatever probabilities you want to calculate, convert into standard normal units and look in the table. So I will open that table and I will show you. Before that, say for standard normal distribution, we have tables that provide area under the curve for any given 2 points. Say for example, I'm taking 2 points here. So what is the area under this shaded region? What is the area for this? How to get this one? So what I will do, I'll open that table now. So in this table, you look at the thing sketch. They have shown it like this, 0 to Z. For me, what is Z? 2. So what they are telling, for Z value, it is they have given on the left side, but only the first digit is given. If you have one more digit, say for example 2.53, how to refer that? For the second digit is given at the top. Say 2.53 means you have to come here, 2.5, this particular row, and you have to come here, the last one where I stopped. The area will be 0.4943. Now I need for Z is equal to 2. So Z equal to 2.00, that is 0.4772. So this how you have to read this table. Now we'll come back to it. That value I have written 0.4772. So given any problem, this how we'll tackle it. We will convert into standard normal units and read the area. And this enables probability calculations. Now we are entering into more logical setup. Tests based on normal distribution. So I am going to give you a general framework how exactly testing works. This will be explained only for normal distribution. Similar way we can do for t and chi-square. That there will not be explaining directly. We will be solving the problem. We can generalize whatever we talk here to those tests also. Say let S be a statistic, means a function of sample observation. For example, arithmetic mean. Assume that S follows normal with mean mu S and standard deviation sigma S. So here, this needs a lot of explanation. Please listen carefully. Say from a population, if you are drawing a sample of size 10, population may be of size 500. There can be large number of different samples drawn. Assume that all such samples are drawn and the mean is calculated. So large number of mean values are there. We prepare a frequency table and draw a frequency curve. That curve will be like this. This is what in short it is saying. So we are assuming that the statistic S will follow normal with mean mu S and standard deviation sigma S. So Z we can calculate further. From this S, I can subtract the corresponding mu, divide by the corresponding standard deviation to make it standard normal. Now, the process and logic of testing. Consider a null hypothesis and an alternative hypothesis. This will suggest an S. For example, the problem of job stress we considered earlier. In that problem, actually, females had job stress 7.1. Males had job stress 6.3. So that's the mean. They were mean values. Okay. If H0 is that female and male population means are same, that is mu1 is equal to mu2, then our interest is in the difference between two sample means. Thus we select x1 bar minus x2 bar as the sample as a statistic. So we can convert this into standard normal units. So Z will be equal to S minus mu S by sigma S. So here, this is your S, and this is your mu S, and this is your sigma S. Now, under null hypothesis, we get Z equal to this, means mu1 is equal to mu2. So mu1 minus mu2 will be 0. So this portion vanishes. So x1 bar minus x2 bar divided by square root of sigma 1 square by n1 plus sigma 2 square by n2. So this formula we get. How we got it? We have assumed that there is no difference between the two population means. Under this null hypothesis, we got this new formula. Now, on calculating this, if the value is extremely large or extremely small, there are two possible conclusions. One, H0 is correct, but a rare event happened. Say how the extremely large is rare. Say for example, consider the normal distribution. Say large values are here and small values are here because this is 0. So largest values are here, smallest values are here. The corresponding area is a probability. So small probability, so rare event. Similarly, on the left side, small values are here. Corresponding area is very small. So probability is small. That is why we say that a rare event happened, because value is extremely large or extremely small. Now, another possibility is that H0 we have used to calculate Z may be wrong. Where we have used, let us go back and see. Say here we have used this H0 to simplify this into this one. This part was removed because of this H0. Now what we are telling, if it has become like this and a rare event, the chances are that H0 may be incorrect. So one explanation is that a rare event happened. Another explanation is that H0 is incorrect. But we will take this stand. Since rare events are rare, it is more logical to conclude that H0 is incorrect and we reject H0. That means ultimately what we are doing on calculating if it belongs to the tails and it indicates a rare event, we will reject the null hypothesis. Otherwise, if it falls in this region, we will accept the null hypothesis. Now, here I have simply put one line and I said everything beyond that is large. Another line I put here, I said everything beyond this is small. Now, how shall I decide scientifically where is the cutoff point here, where is the cutoff point here? For that, there is a process, the process of deciding the extreme values. And now, we say earlier what I said, I put a line here, beyond that I said large values. I put a line here, beyond that I said small values. But how will you decide scientifically that cutoff point? For the process of deciding the extreme values, look at this one. Set follows standard normal. Extreme values falls at the tails. Consider the areas at two tails equivalent to alpha by 2. The corresponding Z, get the corresponding Z values. The region between them is acceptance region and the regions outside are rejection region. I will explain what it is. Look at the curve here. Say suppose if alpha is 0.05, alpha by 2 will be 0.025. I have put at both the ends. Okay. Now, say this curve below that total area is 1. Area to the right side of this line is 0.5. Area to the left side of this line is also 0.5. So this from 0.5, if I subtract 0.025, what I get? 0.475. Okay. So that means this region is 0.475. Okay. Now I look into the table where this 0.475 comes. Say here, I'll mark it here. See, 0.475 comes. Corresponding Z value is 1.9 and second digit is 6. So 1.9 plus 0.06. So 1.96 I get. So I write that 1.96 here. And since it is symmetric about the origin, the value at this point is minus 1.96. So the region between them is acceptance region, and regions beyond that are critical region, or it is also known as region of rejection. Now the decision rules. No, that is all. A decision rule here say if our null everything depends on the alternate hypothesis. How will you decide about this cutoff point? First, you have to look at what is the alternative hypothesis. Alternative hypothesis is not equal to mu naught. That means that either it is greater than mu naught or it is less than mu naught. Two possibilities. So both the tails should be open and mark at both the tails divide alpha by 2, put alpha by 2 here, alpha by 2 here. Between them is the acceptance region. What lies beyond that is the region of rejection. Now, if it is greater than mu naught, okay, the whole alpha will be put at the right end, and from that point to this end, everything is acceptance, and what lies beyond that is rejection. Third possibility, mu is less than mu naught, so it will be marked at this end, whole alpha is there, and this region will be acceptance, and what lies beyond is rejection. So this is how we will decide. Please remember it throughout. When you want to, in every question, you will have to draw this sketch. You have to mark the cutoff point here, acceptance region you have to mark, rejection region you have to mark. It all depends on two things: what is alpha and what is your alternate hypothesis. So if the alternate hypothesis is not equal to, it implies two possibilities. So two tails are marked. Alpha is divided by 2 and put at the both ends. If it is greater than type, only right side, whole alpha is put there. If it is less than type, only left side, whole alpha is put. So this is how we can remember this. Now, procedure of testing. Just note down the available information and specify the level of significance. Usually the question will be in words. You have to write in notations, whatever you get it. Specify your null and alternate hypothesis. Obtain the decision rule, means you have to draw that curve, look to the table, get the cutoff point, mark the acceptance region, mark the rejection region, and then calculate the test statistic. For every test, there will be one formula for test statistic. Use that, calculate them. And then if the calculated test statistic belongs to the critical region, reject H0, otherwise accept H0. These 5 steps which I am giving, it is common for not only Z test, but also T test and also for chi-square test. All testing procedure will follow this. Only thing is that test statistic will vary, and also the nature of the curve also may vary. That I will explain at that time. But this is the general procedure of testing. Now we'll start with the Z test. Now under Z test, there are 4 tests. One is test for mean. That is when we are dealing with only one population, one sample. That sample value is getting compared with some standard value. You have to use this. Here, the null hypothesis will be mu is equal to mu naught. Alternate can be one among these 3. Mu not equal to mu naught, mu greater than mu naught, mu less than mu naught. And test statistic formula is very simple. X bar minus mu naught. Mu naught means mu under the null hypothesis. So whatever you specify here, the same thing have to be written here. And sigma is the standard deviation. This is the sample mean, and this is the sample size. These I have written here. And limitations are there. It is necessary that population variance sigma is known, and the test is accurate if population is normally distributed. Example, say mean age at school admission is 5, and it is less than 5 will be the alternative. Usually such problems do come across for social workers, and if you have collected a sample and if you find that it is less than 5, then it need to be tested. At that time you can keep this as your hypothesis and go for the testing. So I will give you a problem now. In an income survey, the mean income of a community was found to be 1,600. The sample size was 40, and the standard deviation of the population is 80. Test the hypothesis that mean income of the community is 1,700 Against that, it is not 1700 using a level of significance 0.05. So as per our procedure, first we have to write down the given things in notation. That is step number 1. So here it is talking about an income survey. Mean income is 1600. So we'll write down here, given that X bar is 1600. And the standard deviation is of the population is 80. So we'll write down here sigma is 80. Sample size is 40. We'll write here n is equal to 40. Now we need to write the null hypothesis and alternative hypothesis. So okay, of alpha is given, level of significance is 0.05, that also we have written. And we have to write the null hypothesis. What will be the null hypothesis? Mu is equal to 1700. And alternative will be it is not equal to 1700. So these things will copy to the next page. I have copied. So step 1 is over, step 2 is over, step 3 decision rule. We have to mark in this one, say here alternative hypothesis not equal to, that means both the tails should be marked. Alpha is 0.05. So that 0.05 is divided by 2. 0.025 is marked here. So the cutoff value already I have demonstrated in the earlier exercise. I think you will remember it as 1.96. So between this is the acceptance region, beyond them are the rejection region. So what is our decision rule? It is like this: accept if calculated z falls between minus 1.96 to plus 1.96. Reject otherwise. Okay. Now calculate the third step also over. Fourth step, Z score. This was a formula given, simple formula I said at that time. X bar is 1600. Mu naught, that is mu under null hypothesis, that is 1700. Sigma, that is given here 80, that is written. N, that is 40, here it is given there, that's also written. So now 1600 minus 1700 minus 100. This 80 by square root of 40. Square root of 40 is 6.324. So this is the denominator of the denominator. That goes to the numerator. So minus 600 by 80, you get minus 7.9. Now this minus 7.9, where does it fall? Say at the center it is 0. These are the negative values. Minus 1.76 minus 7. It will go far beyond and it belongs to the rejection region. So we'll decide this way. We reject H naught as a calculated value of Z falls outside this region, minus 1.96 to plus 1.96. Okay, I'll solve the next problem. Similar thing, but some modifications. In an income survey, the mean income of a community was found 1600. The sample size was 40 and standard deviation was 80. Test the hypothesis that the mean income of the community is 1650. Against that, it is less than 1650 using level of significance 0.01. First, let us write down slowly one by one. Say it is about income survey and the mean income is 1600. So we'll write here mean X bar is 1600 and standard deviation 80, that also we'll write here, sigma 80. Sample size is 40, that we'll write here 40. And level of significance is 0.01. So alpha is 0.01. Okay, so this much is given. Now hypothesis. Test the hypothesis that mean income of the community is 1650. That is null hypothesis. Against that it is less than 1650. So mu is less than 1650. So we'll copy this table into the next page. So I have copied it here. Now decision rule. Say here you look at this one, alternate hypothesis less than type. So marked only on the left side. Alpha is 0.01. Here, since one-sided test, whole 0.01 will come there. It will not be divided by 2. So I need now the Z table to refer this one. But Z table, you understand, it is talking about the right side. Here we need the left side. But you can use the property. What is the property? It is symmetric about the origin. So therefore, whatever is true about the right side will be true about the left side. So we will look into the right side of this one. So if I'm, say for example, if I put a line here, okay, I'll use my pen. Say if I put a line here, okay. So this area is 0.01. What is this one? What is this? What is this area? This area, what is this? It will be 0.5 minus 0.01. So it will be 0.49. Okay, I'll just erase this one. And okay, now I'll refer to the Z table. So it is 0.49 I have to refer. So 0.49, where does it come? See, look at this one, 0.4901. That is 2.3, second digit is 3, 2.33. So this is minus 2.33 because they are talking about the right side plus 2.33. Symmetric about the origin, it will be minus 2.33. So this is the acceptance region. This is the rejection region. So what is the decision rule? Decision rule will be if the calculated Z is greater than minus 2.33, accept, otherwise reject. So I'll write that one. Accept H0 if calculated Z is greater than 2.33, reject otherwise. Now Z score, the same old formula. X bar, it is 1600. Mu under null hypothesis 1650, and sigma, that is 80, n, it is 40. So here this difference is minus 50. 80 divided by root 46.324, and when you calculate it, you will get minus 3.95. Say you understand that here it is 0, here minus 1, minus 2, minus 2.33, minus 3.95 will be coming here in the rejection region. We reject the H0 as a calculated value. Z is less than minus 2.33. Now, first type of test is over. Second is a difference between mean values. See, here we are making an assumption. Variances are known and unequal. That is assumed here. So here, between two means, where is the situation for that? Actually, the first problem which I have narrated, where job stress among male and female were there. So mu1 is equal to mu2 means what? The mean job stress of males is equal to the mean job stress of females. Alternative can be any of the three. They are not equal, greater than, or less than. So these are the three possibilities for every test. And formula is little more complicated. X1 bar minus X2 bar divided by sigma 1 square by N1 plus sigma 2 square by N2. So this is this one is mean of sample 1, mean of sample 2, standard deviation of population 1, standard deviation of population 2, sample 1 size, sample 2 size, all things are there. And now limitations. It is necessary that the two population variances are known. Of course, it's a very stringent condition. In many of the cases, it may not be known also. The test is accurate if populations are normally distributed. One example, like I have given earlier, mean age at admission to school is same for boys and girls. Alternative, maybe it is different. Again, this is a problem of interest for social workers. So similar situations, when it comes, you can apply this technique. To understand it further, we'll solve one problem for this. So in an income survey, the mean income of a community was found to be rupees 2,800 with population standard deviation of 150. The sample size was 40. So this is about one community they are telling. So here this will be x1 bar, sigma 1 and n1. Now the second paragraph. In the same survey, the sample of 50 individuals of another community has shown a mean income of 3,000 rupees, that is x2 bar, with population standard deviation 110, that is sigma 2, and this 50 sample size is n2. Test whether the two communities differ in their average income level at significance 0.01. So already I said this is your x1 bar and this is your standard deviation and this is your sample size. So x1 bar, sigma 1 and n1. Similarly about the second one, this is your x2 bar and this is standard deviation of the population and this is your n2. So this is about community 2, this is about community 1. Now test whether the two communities differ in their average income. So okay, level of significance is 0.01, that is written. Hypothesis. First hypothesis, null hypothesis says that there is no difference between the two communities. Alternative hypothesis says that they differ between them. So this will lead to a two-tailed test, please understand. So this alpha, which is 0.01, should be divided by 2 and put at both the tails. So this one I will copy to the next page. I'll copy it, and decision rule I'm writing. Said that 0.01 was divided by 2. I get 0.005, 0.005. Now, okay. Say if this is 0.005, what will be the area here? It will be 0.495. So look in the table, where is 0.495 comes? 495. I think this the 0.4951 I'm getting. So this were 2.5 at the top 8. 2.58. So that is why 2.58 and minus 2.58. So this is the acceptance region, this is the rejection region. Accept H0 if the calculated Z falls between minus 2.58 to plus 2.58. Reject otherwise. So these things I have already explained for the previous problems. I don't think it is required to explain further. So let us start calculating the Z score. So this was the formula given. X1 bar 2,800. X2 bar, that is 3,000. So 2,800 minus 3,000. Sigma 1 is 150. So 150 square. Sigma 2 110 is square. N1, N2. N1 is 40, N2 is 50, 40, 50. So when I calculated it, I got minus 7.05. Where is the center? It is 0, minus 1, minus 2, minus 2.5, 8, and then minus 7.05 will be here in the rejection region. So we reject H0. As I calculated, Z value falls outside 2.58 to 2.58. So next we'll go into proportions. So the meaning of the word proportion is the number of something when compared to the whole. As say for example, literacy rate. How do we say that literacy rate? We'll say that literacy rate of Maharashtra is 90%. Means if we have 100 people, 90 do have literacy rate. So similarly, any particular characteristic, what fraction of the population possesses that? That is a proportion. So all the time we may not be dealing with measurable entities. We may be dealing with some variables for which answer is yes or no. How many have given the answer yes out of the total? That is a proportion. So in that case, how will you go for testing? So here, please understand that the small p is always representing the population proportion, which is not known to us. So null hypothesis can be like this. Small p is equal to a particular value. Alternative can be either this or this or this one. And Z formula is this: P minus P naught divided by square root of P naught Q naught into N. Now this P naught comes from the null hypothesis. What is Q naught? 1 minus P naught. So here I have given all this. Small p is population proportion. Capital P is sample proportion. Small p naught, specific value of population proportion. Q naught is 1 minus P naught. So it has limitations are that test is approximate and assumes that the number of observations in the sample is large. When for a small sample, we cannot apply the proportion test at all. Proportion test, wherever it is used, you need a large sample. Example I have given, literacy rate of Kolhapur is 0.9. Alternate hypothesis, literacy rate of Kolhapur is less than 0.9. We'll solve a problem. In a sample of 100 people selected from a city, 62 have shown awareness regarding Pradhan Mantri Suraksha Bima Yojana. Test the hypothesis that awareness proportion in the city is 0.6. Against that, it is more than 0.6 at a level of significance 0.05. So here, in a sample of 100 people selected, 62 have shown the awareness. So what you have to write is sample size is 100, 62 by 100, that is the capital P. What is capital P? Proportion in the sample. This is talking about the sample. So capital P for the proportion in the sample. So 62 by 100, 0.62. So 62.62 is the proportion who are aware about this scheme. Now that tests the hypothesis that the awareness proportion is 0.6. Against that, it is more than 0.6. At level of significance 0.05. So alpha is 0.05. So null hypothesis will be it is equal to 6.6. Alternative hypothesis will be it is more than 0.6. It is also written. So we have got all the given things. We have got the hypothesis. Copy it to the next page. And now the decision rule. Say this greater than type. So we will mark the right tail. Alpha is 0.05. And here this value is 1.65. How it has come, I'll explain. Say this side, it is 0.5. So 0.5 minus 0.05, 0.45. So in the table, where is that 0.45 coming? Say here you can see 1.6, second digit 5. So that 1.65 was written. So anything falls on this side, we'll accept. Anything falls on this side, we'll reject. So this is the rejection region. Accept H0 if the calculated Z is less than 1.65. Reject otherwise. Now Z score. Z is equal to P minus P0 divided by square root of P0 Q0 by N. Say this is the sample proportion, which is 0.62, that is written here. This P0 comes from null hypothesis, 0.6, that is written here. P0 into Q0 means 1 minus 0.6 is 0.4. So 0.6 into 0.4. N is 100. So this I have calculated, I get 0.408. We accept H0 if the calculated value of Z is less than 1.65. So, we accept H0 as a calculated value of Z is less than 1.65. So this is 0.408, it falls here. Okay, next, last criteria, difference between proportions. Suppose there are two populations and two different proportions, then how we are going to deal that? So null hypothesis will be like this, alternative hypothesis will be like this, Z value will be this, where this P has to be calculated first by this formula. What is that? N1 is a sample size from population 1. P1 is a proportion in population 1. N2 is a sample size of population 2. P2 is a proportion in sample from population 2. So with this formula, we have to calculate P, and 1 minus P will be Q. So those things I have explained here completely. And limitation is that the test is approximate and assumes that the number of observations in the two samples is large. Null hypothesis is that there is no difference in literacy rate between the genders, and alternate hypothesis is that literacy rate differs between the gender. Here what we are doing, male population is considered as population 1. Female population is considered as population 2. So in each one there is a proportion of literacy, that is P1 and P2, small p1 and small p2, and we need two samples and we proceed from there. So we'll take a problem on this. In a sample of 185 people from a rural area, it has been found that 120 were aware about the need of vaccination. In the same survey, out of 150 people from urban area, 120 have shown awareness of vaccination. Test the hypothesis that awareness differs between urban and rural people at 0.05 level of significance. So we'll concentrate on paragraph 1. Say this is about rural population. Sample size is 185. And out of that, 120 were aware about the need of vaccination. So what is the proportion? 120 divided by 185. 120 divided by 185. Similarly, now second one, population sample size is 150 and proportion 125 divided by 150. Now alpha is 0.05. Now null hypothesis will be there is no difference between urban and rural population. Alternative hypothesis is that there is a difference between the two. Now we'll copy this table, and for a decision rule we'll mark it like this. This is not equal to means both the possibilities, so left end and right end both are marked, and alpha is divided by 2, so I get 0.025 here, I get 0.025 here. And this already we have referred the table many times. It is already 1.96 and minus 1.96. So this is the acceptance region. This will be the rejection region. Now, accept if the calculated Z falls within minus 1.96 to plus 1.96. So whatever we have marked, I have written here. Reject otherwise. Now the calculation part, follow it very carefully. Say I've already told you, first we have to calculate this P, and that is N1 into capital P1, N2 into capital P2 divided by N1 by N2. So 185 is N1, 150 is N2, this one and this. Okay, so those are entered everywhere, and capital P1 I have got 0.649, that is written. Capital P2 I have got 0.833, that is written here. So I have calculated this, I get 0.73. 1 minus 0.73, 0.27. So I got P and Q. Now Z formula. So P and Q are calculated. Those are written here. N1 is 185. That is written here. N2 is 150, and that is written here. Okay, and P1 minus P2. So P1 0.649 minus P2 0.833. That's also written. So we have substituted, calculated, and the answer is minus 3.841. Say 0 is here, minus 1.96 is here, minus 3.841. It will come somewhere here, the region of rejection. So it will be rejected, and we reject H0 as a calculated value that falls outside minus 1.96 to plus 1.96.